Hello, and welcome to the CCNA Routing and Switching course offered by Simplilearn. The previous lesson focused on Internet Protocol version 6. This lesson focuses on Dynamic Host Configuration Protocol, DHCP, Network Time Protocol, NTP, and High Availability. Let us begin with the objectives of the lesson in the next slide. By the end of this lesson, you will be able to explain the different aspects of DHCP, configure DHCP client, configure Network Time Protocol client, explain the concept of high availability, describe the different protocols. Let us start with DHCP. A Dynamic Host Configuration Protocol DHCP server provides IP addresses to clients such as PCs and printers that request them. A Cisco router can be a DHCP server or a DHCP client with no additional software. A branch office router can receive a DHCP address from corporate headquarters. A home router receives a DHCP address from the Internet Service Provider ISP. Both the branch office router and the home router can then function as DHCP servers to the devices on the LAN. DHCP makes a network administrator's life easier. If DHCP is not there, a static IP address should be manually configured to each PC, and the network administrator would be involved in each office add, move, and change. Another advantage of DHCP is that it conserves addresses because devices that are not active do not consume IP addresses. A Cisco router can act as either a client or a server of DHCP. No additional software is needed. It receives address from the DHCP server. In the next slide, let us discuss how to configure a DHCP client. Enter the command IP address DHCP to configure a DHCP client. The DHCP option takes the place of a specific IP address and mask. This command is configured on the interface that the router expects the DHCP address to arrive on. This is the interface closest to the DHCP server in terms of routing metrics. In the image shown on the slide, assume that the branch office router is the DHCP server and the PC is the client. The IP address DHCP command is configured on the router's interface E0. In the following slide, let us understand how to configure a DHCP server. To configure a DHCP server on the router, ensure that the service DHCP command is in the running configuration. This is the default configuration. A DHCP server provides more than IP addresses. It can provide any or all of the following: IP address subnet, default router, domain name, DNS server, NetBIOS name server, and/or lease information. The client leases an address from the server. The lease is valid for a limited period of time. Excluded addresses are in the subnet, but are not available to assign because they are already in use for the router interface, switch management, servers, and/or other devices with static IP addresses. These devices have manually configured addresses because other devices need to reach them. If their addresses are changed, there would be no connectivity. In the next slide, let us look into Network Time Protocol, NTP. Network Time Protocol, NTP, is used to synchronize the clocks on network devices. This is important for two reasons. System messages contain timestamps that list the time that each message is generated. Troubleshooting a problem that involves more than one network device is difficult when the timestamps cannot be reconciled. In addition, authentication most often requires synchronization because it specifies timeframes for access and uses timestamps for security associations. One router in the network becomes the NTP server. All the other devices become clients and obtain their time from the server. The server obtains time information for a source outside the LAN, just as your PC does. A Windows PC obtains its time from the website time.windows.com. NTP uses UDP over port 123. It is a slow protocol. The formation of NTP associations can take a long time. NTP clients are configured, at least at the CCNA level, with the single command shown on the slide. In the next slide, let us focus on high availability. High availability means that network devices, or the network in general, is up and available for use as close to 100% of the time as possible. Earlier in this course, we discussed redundancy of devices and links. This redundancy can help achieve high availability, but high availability is not achieved by adding more hardware to the network. Let us view the image on slide and understand why. In the image, all the PCs are in subnet 192.168.1.0/24. They all have a default gateway of 192.168.1.4, the FA00 interface of router 1. If FA00 fails, none of the PCs are able to reach the network. Let us continue our discussion on high availability in the next slide. In the slide, let us see what happens if another router, router 2, is added. Once another router is added, half of the PCs will be assigned a default gateway of 192.168.1.4 and the other half 192.168.1.5. Now, if FA00 fails, only half of the PCs are unable to reach the network. With only one router, all the PCs could not reach the network. Adding another router is an improvement, but adding more routers is very expensive. Also, this is not an ideal solution for 100% network access to the PCs. As shown on the image, device redundancy by adding routers will not completely solve the failover problem. Some kind of backup default gateway is required. Let us discuss backup default gateway in the next slide. High availability delivers redundancy of function. Another device provides the same function as the default gateway that failed. An additional router is required, but software must also be added to handle redirecting the PCs to a new default gateway. This software is called First Hop Redundancy Protocol, FHRP, because the default gateway is the PC's first hop from a routing point of view. The iOS provides FHRP software, Hot Standby Routing Protocol, HSRP, and/or Virtual Router Redundancy Protocol, VRRP. Cisco also offers another FHRP, Global Load Balancing Protocol, GLBP, that allows for up to 4 default gateways with load balancing. Note that these backup default gateways still must have an interface in the same subnet. This requires a switch between the routers and the end devices. This is because each router interface is a separate subnet. In the following slide, let us look into HSRP. In Hot Standby Routing Protocol, HSRP, the default gateway is a virtual router. It has a virtual IP address and virtual MAC address that can be used for Address Resolution Protocol, ARP, as a real router does. End devices are assigned the virtual router's IP address as their default gateway. HSRP directs the end devices to use the appropriate real router. Each HSRP group, also called a standby group, has one active router that acts as the default gateway and one or more standby routers that can take its place if the active router fails. The active router is chosen by the highest priority, which is a configured value. At the CCNA level, you are not expected to configure HSRP. However, you should understand the verification output. Let us look at some in the next slide. Here the show command output shows that there is one standby group on RTR1, Group 1. RTR1 is the active router for that group. The virtual IP assigned to the end users is 1.0.0.253. In other words, this is the end user's default gateway. Take a moment to review the output. Now let us look at RTR2. RTR2 is the standby router for Group 1 because its priority, 90, is lower than RTR1's, 110, for that group. The real interface that is serving as the default gateway and handling routing requests is the IP address of an interface on RTR1. Take a moment to review the output. In the next slide, let us discuss Show Standby command. Entering the Show Standby command on RTR2 provides even more information. Now you know the virtual MAC address as well as the virtual IP address. As seen on the image, the highlighted line says, Standby router is local. The local router is the router that we entered the command on. So RTR2 is the standby, not the active router. Take some time to review the output. In the next slide, let us look into VRRP. VRRP is a standard protocol, unlike HSRP, which is a Cisco proprietary protocol. The configuration and function are similar to HSRP. A VRRP group has one master router and one or more backup routers, a change in terminology from the active and standby routers of HSRP. To verify VRRP, use the Show VRRP command. The output shows the virtual IP and MAC addresses and whether this router is the master router or a backup. It is similar to the output from HSRP's Show Standby command. In the next slide, let us discuss Gateway Load Balancing Protocol. Gateway Load Balancing Protocol, GLBP, is a Cisco proprietary protocol. HSRP and VRRP provide a backup default gateway. However, it would be better if the backup could share the default gateway traffic, even when there is no failover. This is load balancing. GLBP can be used to share traffic across up to 4 gateways. The Active Virtual Gateway, AVG, is a router elected by the GLBP group that responds to all ARP requests from the end devices. The gateways, called Active Virtual Forwarders, AVFs, use the same virtual IP address, but a different virtual MAC address that is assigned by the Active Virtual Gateway, AVG. GLBP load balancing defaults to round robin. This means that each AVF takes a turn in succession. To verify GLBP, use the Show GLBP command. This shows information about the AVG active and the AVF's forwarders. Let us move on to the quiz questions to check your understanding of the topics covered in this lesson.